recording has started as well. So yeah, you should be able to see the slides right now. Someone has turned on his microphone, I think. There are some noise, background noise. It's not from me, I hope. Okay. Last time we have started to talk about, actually we covered the heap data structure and its implementation, right? Let me go back. There is some problem here. Okay, yeah, let me. Okay, that's better. Okay, last time we have talked about the heap structure and how to insert and remove heap structure and what is the performance of this insertion and removal operations. And we have seen that both can be performed in logarithmic time using array, right? Binary heap is implemented on arrays, and both operations, insert and remove operations, takes logarithmic time in this structure. Okay, we are not gonna define heap as an abstract data type, or we are not gonna define heap as implementation of abstract data type, but we are gonna use heap to implement a special kind of queue, which is called priority queue. It is like a queue. Priority queue is like a queue, so it provides the operations for queue. So we are gonna define priority queue as implementation of queue interface, and we are gonna implement priority queue using heap. As I said, heap is not an abstract data type. It specifies the internal data organization and the operations. So it's not abstract, but we will use that data structure to implement priority queue. Okay, so we will not create a heap interface or a class that implements queue, but we are going to call it priority queue as in Java. Java has a priority queue class that implements the queue interface, so we are going to follow that convention. And instead, we will incorporate the algorithms of heap when we implement priority queue. And of course, we are going to see heap sort later on. In heap sort, we are going to use the algorithms of heap in heap sort. That is a special kind of sort operation that we are going to see later on. Okay, a regular queue is FIFO, means first in, first out structure, but sometimes FIFO queues are not enough, are not good way of doing things. For example, for some waiting lines, for example, print queues. In print queue, sometimes it's better to perform printing of the print jobs in print queue in a special order in an order that prints the job that has highest priority. So in that implementations, we can use priority queue instead of regular first in, first out queue. For example, when a short document is arrived after a long document, it has to wait for a long time for a long document to print. And if after a document with 1 or 2 pages will be printed, if you use FIFO, but instead you can use priority queue data structure and use the size of the document as priority information. And if you use priority queue, you access the lowest priority or highest priority, actually, the smallest job first. So when you take out a job from print queue which is implemented as priority queue, you take out the job with the smallest number of pages as opposed to first item entered, and print the short jobs first. This kind of queue, short job first queue. And we are gonna talk about short job first queues in operating system as well. Okay, so for example, if we have 2 jobs currently in priority queue of printer as a printer queue, and then we insert a job with 3 pages, it's gonna be deleted after this and before 4-page history paper. And we insert another print job with 1 page. It's gonna be printed after this 1-page web page and 3-page lab 1 document, right? So as you see here, the jobs are kept as sorted order based on the page number of pages in the job, right? We do not need to keep them sorted order. You can keep them sorted order. You can use sorted array to implement priority queue as well. But if you use sorted array for the priority queue, the performance will be lower, at least for insertion operation. But in priority queue, in Java, and as we are going to implement in a minute, the priority queue is implemented as heap, not as sorted array as in here. Okay. Java provides a priority queue class, as I said, which implements queue interface. Remember queue interface from FIFO queue. These are the methods in queue interface. The behavior semantic of these methods are changed in priority queue. The operations are same, the syntax are same, since it implements the queue interface. The same operation should be implemented, but the behavior is different, semantic is different. For example, in offer operation, semantic is same, but in remove operation, semantic is not same. As you see, it removes the smallest entry and returns it if the queue is not empty. In regular queue, the element that is inserted first should be returned, right? Not the smallest entry. Similarly, poll, the syntax has been changed. Smallest entry is returned. And if there is no such element, if the queue is empty, it returns null. Similarly, peak, it returns null if the queue is empty. Otherwise, it returns the smallest entry. Semantic is changed. Again, element returns throws a exception if the queue is empty and returns smallest entry without removing it. Of course, if the queue is not empty. So the semantic is changed. Semantic is changed for all these operations. Only offer operation has the same semantic, same behavior. So you should be careful about it. Okay. We are gonna implement prior to queue just like heap, since in heap the smallest element, removal of smallest element and accessing smallest element is fast, remember? So we can use prior to queue algorithms to implement heap algorithms to implement prior to queue actually. Remember, it takes logarithmic time to insert and remove. So when we look at these operations, all these operations will take logarithmic time to insert, remove, or poll will take logarithmic time. Without removing the element to return the smallest entry is at the root, so we can access it in constant time. So element and peak operations are constant time operations using heap, you remember, right? In Java, we have a priority queue, as I said. It keeps an array of objects as an internal representation to implement heap structure actually. But in this book, in our textbook, the heap structure is implemented using array list in priority queue. KW priority queue will use array list as underlying data storage and used heap algorithms over this array list to implement KW priority queue. Okay, this is the design of KW priority queue. It will keep an array list to store the data elements that are stored in the priority queue. It is like an array, as you all know. We have defined heap using regular array, but array list is very similar. So we are not going to be able to, we are not going to have any trouble implementing heap algorithms on array list, right? And we are going to use a comparator if the elements E are comparable, we can use comparative method of the objects to compare the elements, since the elements have to be compared to be able to get the smallest entry, right? Or we can talk about comparator to compare elements. It is optional if you would like to change the order, definition of the smallest, different than the natural order of compare to method in objects, if you would like to define smallest differently than compared to method of the object, then you can use comparator object. Comparator interface just defines the compare method, which compares the elements. So you can write a class that implements the comparator interface, and you can provide that comparator as a parameter to constructor to be able to use that comparator instead of using comparator method. Okay. So we have two constructors. Both construct heap-based priority queue. And if we construct using no parameter, natural ordering of the elements is used using comparator method. If you specify a comparator, then the compare method of this comparator comp will be used to compare the elements and to find the smallest element. So compare method of the comparator determines the ordering of the elements, right? So these are two constructors. Also, we will define a compare method, which is private method, which takes two elements and returns an integer based on the order of these two elements. It will return negative value if the object on the left is less than on the right. 0 if they are equal, or positive value if the left is greater than the right. Right? So it is a natural way of doing it. And this compare method will be used the comparator, or if it is defined in the constructor, and it will use comparator method of the objects if it is not defined. Okay, the swap is what you know, the two elements of the array list will be swapped using this private swap method. Okay, in the slides we have the implementation, but I would like to go to this code on Notepad. It is easier to go over. I can show more on this thing. So KW prior to Q is defined as a generic class which implements the queue interface and extends the abstract queue. Since queue interface has several methods, abstract queue implements some of them with the help of the others. We only need to implement a subset of the queue interface if we extend the abstract queue, as you all remember, right? And we keep an array list to keep the data in the priority queue. Of course, we are gonna use heap algorithms, so this array list will be handled specially to represent heap. We have to keep a comparator, which is initially null. As I said, we have two constructors. The first constructor is a non-parametric constructor, and it will just create an array list, and it keeps the comparator to be null. So if the comparator is null, we just use compare method of the objects, as I said. The second constructor has two parameters. One is the comparator, as I said. The other is cap for capacity. As you remember, while you are creating a new array list, you can define initial capacity. Here with this constructor, we can define the initial capacity as well, and the comparator to be used for ordering of the elements in the priority queue. So initial capacity of the priority queue is the cap, and the comparator to be used in this priority queue will be comp. As you see, if the capacity is negative, 0 or negative, we will throw an exception. You see here if cap is less than 1. Otherwise, it creates an array list and assigns the parameter comparator to comparator data field. This is the offer method. Offer method assumes that the array is in heap order, and after the insertion, the priority queue will have the item and will be in heap order as well. The item is in the priority queue, and the array is in array list is in heap order afterwards. This is precondition and postcondition. And it has just one parameter item to be inserted, right? Okay. In this offer method, remember we insert the element at the end of the priority queue, at the end of the array, so we can use add method of the array list. Add method will insert at the end. Of course, we have to use two indices, parent and child, which are initialized as here. You should remember from the previous class. And in a while loop, we swap the parent value with the child value if their order is not correct. As you see in the while loop, we check the parent data with the child data. If the parent is greater than the child, we perform the while loop, swap the parent with child, and update child and parent indices, right? And we continue until the parent is good. Oh no, child is root, until the child is root, and there is an prior order heap order property is violated, right? Heap order property is violated if the parent is larger. It should be smaller, right? So as you remember, this operation takes logarithmic time, since the height of the tree is logarithmic, and the operations here in this while loop is constant time, and the number of times this while loop will be executed is at most the height of the tree, and at the smallest number of times will be 0. So that's why we cannot say theta log n for the running time, but we can say O log n for the running time of this offer method. Here is the poll method. As you see, post condition and precondition, the array list is in heap order before the running of the poll method. And after the poll method, the smallest item is removed and the elements are heap order and heap order property is preserved, and it returns the smallest priority value. Okay. There are special cases. If the heap is empty, we can say that there is no element that should be returned. So it returns null. The smallest element at this at position 0, so the position 0 element is saved as result. If there are just one element, that's another special case, we remove that element and return result. That's a special case. Otherwise, we have to perform the general operation. We take the last element, we take out, remove, and insert it at the set it the first element with the last element. So we move the last element to in the place of the first element, right? We set the first element, remove the last element. So all the operations here will take constant time. Removing last element and setting element 0, the first element will be constant time, right? So the last element is moved to the first position in the place of the smallest element. That would violate the heap order property. So we have a while loop to fix the heap order property here. We start with parent as root. Left child is defined set with parent value, right? We all know that left child is 2 times the parent plus 1. Right child is 2 times parent plus 2, or left child plus 1, right? If there is no left child, we just break, since we get if there is no left child, the parent is a leaf. We get out of the while loop. If there is left child, we get the right child, and min child is set to be left child first. And if there is a right child, and if the right child is smaller than left child, we update the min child to the right child. So until here, we find the smallest child in min child. As you see the assertion here, min child is the index of the smallest child. And afterwards, we move the smaller child up heap if necessary. We compare the smallest child with the parent, and the parent, if the parent is greater than the smallest child, we swap the min child with the parent and update the parent. Otherwise, if the so here we check the whether the heap order property is violated or not. If it is violated, we perform the swap operation. If the heap order property is not violated, we just break the while loop and we return result. So in this while loop, starting from the root, as the heap order property is violated, we move parent down to its swap it with the minimum child, and we continue like that until the parent is leaf or the heap order property is not violated. Okay, this is how the poll method is implemented. As you remember, here again we start from the root and go down until the leaf. So the number of times the while loop is executed will be will depend on the height of the tree. Height of the tree is logarithmic, right? And in the worst case, the number of times this while loop will executed is h, and in the smallest number of times the while loop is executed is 1. So the best case is constant time, worst case is logarithmic time. That's why we say the running time is big O log n, right? This is the compare method. In compare method, we use the compare method of the comparator if the comparator is not null, or comparator method of the element if it is null, right? If the comparator is not defined. So the function will compare two elements either using comparator objects, compare method, or their natural ordering using comparator method. Okay. If the comparator is null, left and right should be comparable. It should provide comparator method as a precondition. And we have two parameters, two items, and return values depend on the order of these two items. It will return negative if the left is less than right, and etc. Okay, both compare method and comparator method will provide this value, so we return their return value right away. Swap method will swap two elements in the array list, so it is easy, constant time operation. Again, this compare method is constant time. Compare method is constant time as well. Size can be handled by using the size of the array list, right? The size of the array list will return the number of elements in the array list, and the size of the priority queue is the same. So we delegate the size method to array list size method. We delegate the iterator method to iterator method of the array list as well. So by using this iterator, you can go through the array list. Of course, in this array list, what we know is only the smallest element is the first element, but we are not say that the other elements are sorted. They are not sorted, but we know that there is an ordering, heap ordering between parents and children, parents and each children of it. Peak should return as smallest element, which is at position 0. So we can get the element at 0 position and return right away. So this is a constant time operation as well. So these are all the methods that are implemented in the book. So I'm gonna stop here. As you see here, we have prior to queue clause, offer, poll, iterator is used, and size methods are delegated to array list, as you remember. Is empty is simple. It checks whether size is equal to 0 or not, and it's inherited from abstract collection. Actually, we have defined prior to queue to extend abstract queue. Abstract queue extends the abstract collection, so it is inherited from there. Other operations, peek and remove, can be implemented easily using other operations, right? Like poll, etc. So we have talked about construct that use comparator as a parameter, right? Compare method of the comparator. Okay, this is compare method of the priority queue that we have talked about, and we are here now. Time is up, so let's have a break here, and after the break we are going to talk about the example applications of priority queue. Okay, let's have a break for 10 minutes. I will stop